last time we were looking at the anatomy of a simple interactive input-output program. This program that prompts you to enter in a certain number of miles. It reads it in, and then it computes how many kilometers are in those miles, and then it prints it out. It's interactive. It sits there and waits for you to input, type, enter, and it takes that out, that input and processes output. All right. So to pick up where we left off, we were looking at the various types of variables that were used in that program and that we'll be using throughout the semester. I'm keeping it simple initially to just these three because I don't want to overwhelm you. These are going to be the three essential ones that we're going to be using to start out with. An integer, or int for short, a double, a floating point number. Integers are whole numbers, positive, negative, and 0. Doubles are positive, negative, and 0 as well, but they can be fractions, 10.5, etc. A char is a single character, like a capital C or a lowercase c. And I mentioned that statically typed means that you have to declare it before you can actually use it. So to show you what I mean by that, let me go ahead and take this line of code where I'm declaring these variables. I'm saying that there's a variable called miles, and there's a variable called kilometers, and they are both of type double. And let me go ahead and move them. Let me move them down here to after I try to read in miles. Now, does the variable miles exist at that point? No, because I've not declared it. And consequently, this will be a compiler error. KMS to miles, there we go. And it'll say miles is undeclared. I don't know what you're talking about, right? Because you declare it at line 20. It exists as of line 20 and throughout the rest of the scope of that program, at least for the main program right here. That's called a variable scope. We say scope because where is it visible, right? If you look through a scope, you can't see the entire world. You can only see what's in your scope at that time. So wherever you declare this, that's the scope of that variable. That's where it exists if I'm looking at it right there. It only exists from line 20 down to line 25. If I move it up here, well, actually, I couldn't move it right here, right? Because I'm not using it before then, but that's kind of weird. I'm just going to go ahead and move it all the way back to where it belongs, all the way at the top, and remove my white space here, right? Now it's in scope. It can see it. It can see it because it's in scope, and it knows about those two variables, right? What are the limitations of these variables, right? Limitations. Integers can only represent values. Where is my, I need to cut and paste it, 2147, there we go. Can only represent values, actually, let me give you the full definition here and spell it correctly. There we go. An integer, or an int, is, here's the technical term, it's a 32-bit signed 2's complement integer. Don't worry about that. Eventually, when you have to take a hardware class, you have to worry about what that actually means and how these things are actually represented in binary. Because computers only understand 0 and 1, right? Low voltage, high voltage, on or off. They don't understand, because they don't have 10 fingers and 10 toes like we do, the decimal system. So we're only given 32 of those zeros and ones to represent this integer. Consequently, we can represent values from negative 2,147,000,000, blah, 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 and 48 and change, right? Up to and including 2.147 billion and 7, right? Why? Because that's how many bits it takes to represent, right? If you take out, if you want a little bit deeper understanding, these two things are equivalent. Oops, I'm typing in the wrong one here. There we go. I'll come over here. These two things are equivalent to 2 to the 31st with a negative out front, right? Less than or equal to x, less than or equal to 2 to the 31st minus 1. Right? So those are those two numbers right there. That minus 1 is important. That minus 1 is important. Why? Because, well, 0's got to be represented, right? So are we going to represent it over here, or are we going to represent it over here? Well, we just chose over here. So we can only represent one less than 2 to the 31st. 2 to the 31st is actually equal to 2.147 billion and and 48. But when we subtract off 1, that's why we get this limitation on the right-hand side, because we have to represent 0 somehow. Why is it to the power of 31? Well, remember, we have a 32-bit signed integer. We've got 32 zeros and ones to work with. One of those has to say negative or positive. So consequently, we're left with 31 to actually represent the number. Now, why is it 2 to the 31st? Think about this thought experiment here. What if I only gave you 2 digits, 0 through 9, to represent a number? What's the maximum value that you could represent? Not 32, not 42, right? Keep going, up to 99. Well, what is 99? I gave you 2 digits, right? That's the maximum value that you can represent. If I think about that in base 2, or base 10, excuse me, that's going to be 10 to the second, the 2 digits that I gave you, minus 1, because you have to start at 0. Likewise, this is the same principle here, except that computers don't speak in base 10. They speak in base 2. And so we have 2 as our base instead. That's just a preview of why it is that way. Understand that for the purposes of this course, you're not going to be able to represent arbitrarily large numbers using the built-in type of integer. There is a limitation. And let me show you one of the consequences of that limitation. Let me come over here and try to create an integer variable. How? Int x. X is a terrible variable name, but we'll talk about variable names and best practices here in a second. I'm going to set it equal to that maximum value, that 2.147 billion and change. There we go. And I'm going to print it out. Printf x is equal to %d, and the line we'll review printing here in a second, x. And now let me go ahead and add one. We haven't gotten to operators and additions yet, but hopefully you can understand this just by me telling you what it is. X is equal to x plus 1. I'm adding 1 to it. So if you added 1 to 2.147 billion and change, then you should get this number right here. Let's see if we do get that number. Right, there we go. And I commented out everything else, so nothing else should run, just this snippet of code right here. Right? And let me go ahead and run it. Oops, yep, A.0. All right, well, I kind of get that number. Right? There is one addition to that, but what happened over here? It's negative, right? That's not correct, is it? Right? It should be positive 2.147 billion ... 48. Why did that happen? Think about the integers, right? They're infinite. This way you've got negatives, that way you've got positives. It goes on forever. Computers are not infinite. Computers have a limited amount of memory. They're a finite amount of memory. You might have several terabytes, maybe terabytes of RAM or gigabytes of RAM, whatever it is nowadays, right? But so you can only represent a small amount of information on a computer, not an infinite amount of information. So we have to reconcile these two systems, infinite numbers versus finite representation. The way that it happens is not a number line, because number lines go off forever in both directions. It is a circle, right? So start here up here at 0 and start adding positive numbers. 1, 2, 3, 4, 5, 6, 7. Eventually you get over here to 2.147 billion ... 47. Start at 0 and start subtracting numbers. -1, -2, -3, -4. Eventually, you'll get to these two numbers sitting down here right next to each other. So what happens at the end of this circle when you add 1 or when you subtract 1? It goes around the other direction of the circle, right? And that's what was called integer overflow, right? Exceeding the maximum or minimum values leads to what's called overflow or underflow. If you go the other direction, right? If you go 2 negative, 2 negative, 2 negative, and then you wrap around back to the positives, you've underflowed your values. Right? So just understand that 2.147 billion and change, that's the maximum value that you can represent. I really want to represent larger numbers. Well, if you want to do that, you're bringing in a library to do it, and that goes beyond the scope here. But it is in one of the advanced activities later on in the semester if you're interested in one of your labs. What I want to look at is floats, right? Or doubles in our case. Here, there we go. I should have gone in on that one. There we go. A double is, again, here's the technical term. It's an IEEE 754 floating point number. Don't worry about that. When you get to a hardware class, you're eventually going to have to look at that standard and see how it's implemented. For us, the real takeaway here is that any float, any double number, only has 16 to 17 decimals of accuracy, okay? So, consequently, you can represent pi 3.14159 ... but only 16 or 17 decimals of accuracy. When you get out further, it starts to be 0 or garbage. It's unreliable. 16 to 17 digits of accuracy is actually quite a bit, and that's enough to do a lot of the stuff. Certainly enough to do anything that you'll do in this course. Again, if you want, I need actually 1,000 digits of accuracy because I'm doing some scientific thing with the Higgs boson or something like that, right? Well, then fine, you're bringing in a library to do it. And the way that libraries work to do it is, oh, I need more precision. I need more precision. Okay, I will allocate more memory for you. I will allocate more memory for you. Eventually, you're going to run out of memory anyway, right? So there, again, you still cannot represent infinite numbers either direction, right? Okay, we'll look at a consequence of this later on. In addition to that, a char is a single ASCII text value. Let me go ahead and show you what I mean by that over here with an example. My initial, char, initial, yeah, there we go, is going to be equal to C, my first name, Chris, right? That's different than lowercase c. Everything worthwhile in computer science is case sensitive. Those two things are not the same thing. It's a single character. Therefore, we use, what kind of quotes there? Single quotes. If I had double quotes, that's not a character. That's going to be a compiler error, hopefully, or at least a warning. Nope, it's a warning. It'll let you do whatever you want, right? But it's going to warn you about it, right? That is a string, multiple characters. Even though there's only one character here, it's going to treat it as multiple characters, which is why it's giving you that warning. Only when I have a single character in there will it compile with no errors. What if I put in multiple characters, my entire name? That's not my initial. Now it's another warning, a different warning, but it's still going to let you do that. C is a programming language that, so there are lots of other safer programming languages, Python, Java, etc., that if you try to do something dangerous, the compiler, the system, whatever, is going to ask you, are you really sure that you want to do that? Right? And that's what it's in fact, I'm not even going to let you do that because it's too dangerous. But with C, it's just going to say, I don't think you want to do that, but go ahead, right? It's your program, I guess, right? So always make sure that you're paying attention to the warnings. In fact, in our hack rubrics, as you start doing actual programs, having warnings is not good. In fact, it'll fail one of the tests in code posts. So make sure that you're addressing all the warnings here. And pretty much a warning is pointing out some sort of a bug there, okay? All right, yeah, go ahead. Good question. So let's go ahead and try to print it out. Printf. It'll probably work here, but it's probably initial is equal to %c and the line. Later on, when we look at memory, we'll understand this a little bit more. Basically, I'm corrupting my own memory, but the operating system is okay with that. It's your memory. You can do with it whatever you want. Go ahead and corrupt it. I don't care, right? Oops, printf. Sorry. There we go. Oh, there. Does it print my initial? C? No. It's probably going to the end of the string here somehow and getting that S right there. But that's just a crapshoot. It's undefined behavior. Anything could have happened. Right? That's just one possibility of something happening. Actually, it's saying that it's overflow. So, oops, cancel that. So it's probably doing something with the ASCII text table. .com, there we go. So when I said ASCII, I didn't define it. Just like I didn't define the IEEE 754 standard or what 2's complement is. But let's go ahead and take a look at what ASCII is. Right? ASCII stands for American Standard Code for Information Interchange. It's very old. I thought it went back to the 40s. I could be wrong, maybe the 60s or something like that. I thought it was from the Eisenhower administration, where they had these QWERTY keyboards, and then computers came onto the scene. We need a way of encoding this keyboard in a computer. So they came up with this table right here. We've got the alphabet, uppercase A through Z, lowercase or A through Z, numbers, punctuation, special things, for example, how do I go to the next line? Remember that it was a slash, and I forget forward slash or backslash? Backslash, and an N, right? What about a tab? A tab is right there, a horizontal tab, right? In fact, you can make your console go ding, right? Well, why do they have a bell in there? Has anybody actually seen a physical typewriter? Or you've seen them in old-timey movies, right? Type, 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 type. You get to the end of the line, what happens? Ding, exactly, right? So why do we have this stuff? Well, because of typewriters, right? And that's what it was at the time. We don't have this just this anymore, I should say. Along came the extended ASCII character set, where they added things with diacritics on top of the A and such. And a little bit more, the Greek alphabet here, probably for mathematics rather than to support actual Greek. This was still not enough, so they added Unicode. Right? Unicode, you'd probably best know it as how do you get emojis, how do you get emoticons. It's an extension to this that doesn't just represent values. I should have mentioned that there's A, but it also has a decimal representation, 65. There's lowercase a, it has a decimal representation of 97. 0 through 127 was all they had back in the 40s, 50s, or 60s. Nowadays, we have millions of possibilities. Why? Because we have Chinese, Japanese, Korean fonts, and thousands of those characters. We have ancient hieroglyphics. We have Cyrillic. We have a whole, all languages of the world are now represented by Unicode, including emoticons or emojis or whatever they're called, right? Same idea here, though. There's just a number representation of it. Unicode's smiley face, right? You can look it up, and you can look up what number it is. There we go. 1F60. Oh, that's the angry face, sorry. Anyway, let's go ahead and zoom in on this. So the happy or grinning face looks like its code is 1F600. That's just a hexadecimal representation. Right? The full Unicode standard allows, I think, 1.6 million different representations of characters and letters and stuff like that, including different colors of those characters. You can add your own if you write up a proposal and submit it. In fact, people have, and some people have been rejected. In particular, the most famous ones that were rejected were the ones that wanted to add Klingon to it. Right? A completely made-up language. In fact, that's why they were rejected, because that's just a science fiction language. Right? We're not going to add that stuff. Right? All right, so we're limited, unfortunately, to the ASCII text table with single chars. You can always, just like we're limited with numbers here, you can go ahead and support emoticons or emojis or CJK fonts or whatever. How? You bring in a library to do it. Right? It's not part of the core language. Some other observations here about best practices for variable naming. Right? So generally, I recommend you follow a lower camel casing convention for variables. Now, do you see what I did there? If you've got a variable name with multiple different words, lower camel casing, what did I do? Everything is lowercase except for the first letter of each subsequent word. The first one is lowercase l, right? Every word after that has an uppercase to it. That's why we call it camel casing. If you look at it, it looks like the hump of a camel on each word except for the first one. And in case you're wondering, there is upper camel casing. There is upper camel casing. That's used in programming languages for classes, object-oriented programming languages. We're not going to use that, though. I'm just mentioning that because, yes, there is an upper camel casing. Right? Alternative is going to be lower underscore casing. Right? And in fact, that's the really old school way of doing it, the classic way of doing it. I'm not recommending that. I'm recommending that you go with lower camel casing. Why? Think about when you're typing an underscore every single time. What are you doing? First of all, you're taking your pinky and you're holding down the shift button. Right? You're going to get arthritis there really quick if you keep doing this. Right? And then you're going all the way across the keyboard to hit that hyphen to get the underscore, right? While you're holding this down. It slows down your typing. It causes your early arthritis, right? And it's just not, it's not a great convention to follow, in my opinion. Now, there are programming languages that use that as the default, or as the default recommendation. For example, Python. And I've had to force my 20 years of training or so of not doing lower camel casing in Python because this is the Pythonic way of doing it. And so I've forced myself to do things Pythonically when I'm in the Python programming language. What else have you seen here, though? If I bring your attention over here to this constant, KMS per mile, that's neither one of those things. Generally, constants are going to have an upper underscore casing. Right? That's way you can really distinguish between whether or not something is a variable. In other words, its value can vary, it can be changed, versus something is constant. It cannot change or should not change. Right? Pi, for example. Here's some examples. Examples of variables, or good variable names. Right? Number of students. Right? I don't know. Miles, right? Kilometers, etc. Right? If it's only one word, of course, it's all lowercase. Examples of constants. In fact, I'm going to take directly from the math library, math.h library. M underscore pi. Right? You don't have to make your own definition of pi. There's already one provided for you in the in the math library. Why did they call it M underscore pi? Math pi. The math library is pi, right? They also have M underscore E. There's that E, exponent, right? 2.71 something, 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 right? You don't have to define your own E if you need to do math stuff with it, right? Or the example that we gave here is kilometers per mile. Right? Okay. So, guidelines for this. Variable names should be descriptive. Right? Variable names should be nouns. Right? Why? Because they are things, person, place, or thing, right? Or a number or a counting of something. They're not verbs. Verbs are going to be when we look at functions, because functions do things. They're actions, right? They're verbs. Variable names should be nouns. Avoid placeholder names, such as foo, bar, baz. Those are the classic ones. I don't know what this stands for. I'm just going to use a placeholder foo, right? Or x and y, right? Now, if you're doing something related to math and you're talking about the x and y coordinates, okay, fine. Maybe x and y are good variable names because you don't actually know what they stand for. In fact, if you go over to your math class, they don't know what they stand for. It's just a number, right? They're thinking about things abstractly. We're not thinking about things abstractly. We're thinking about kilometers. We're thinking about miles. We're thinking about dollars or whatever, right? Our variables have names to them. Math variables don't have names. That's why they use x, y, z, a, b, c, alpha, gamma, pi, et cetera, et cetera. We use proper variable names so that they're descriptive and we know what we're talking about. X, Y, Z, what are those? I have no idea. I'm always having to reread my code over and over again, slowing me down and confusing me every single time. Right? Avoid abbreviations unless they are absolutely understood. Right? So, for example, SSN. What does that probably stand for, or SSN? Social Security number, probably, right? Or what about something like, I don't know, NUID? Everybody here probably knows what that is, but that's because you're from here, you're enrolled at Nebraska, right? Nebraska University ID. You go over to any other state and they're going to say, what the heck is an NUID, right? So depending on context, maybe it's okay, Social Security number. Depending on context, maybe it's not okay. Right? It doesn't. You're not paying by or you're not paying and you're not getting paid by the character. So just make your variables more descriptive. Right? I like Social Security number instead of SSN. Right? But that's more art and guidelines rather than rules. Right? Okay. So more printing and formatting. Right? So recall that you can format in output using printf and placeholders. We talked about that, right? Hopefully. Do you remember the placeholders? Here we go. %d is for integers, %f for floats, and %c for single characters. That's how you can output variable values. You can actually have a lot more control over this, right? You can change the default formatting using modifiers. Right? So by default, %f prints out 6 decimals of accuracy. Right? You can control this using the following: x.yf, or %x.yf, there we go, right? Where x is going to be the minimum number of columns to be printed, and y is the number of decimal places to output, okay? So let's take a look at that over here in this program. Again, I'm going to go ahead and leave everything out there. Let's go ahead and use pi. So printf, pi is equal to %f. Let's just look at the default formatting first. I'm going to output m underscore pi. Note here that that's in the math library. I'm already including it. We're good. Right? If you didn't include this, you might have difficulties. Right? So I'm going to go ahead and include that. Let's go ahead and see what that looks like. So recompile. There we go. 3.141592. There we go. Or 93. Wait a second. From my memory, it should have been a 2, right? Let's look that up. Pi. There we go. Oh, okay. Give me some more significant sig figs here. Significant figures. Come on. All right. Lots of digits of pi. Get rid of that. Get rid of that. 1 million digits of pi. There we go. That's probably going to be enough. 1.314. Let's zoom in on that. I was right. My memory didn't lie to me. It was a 2. Why did it print 3 here? Well, if it's only going to print 6 decimals of accuracy, it's got to make a decision. What do I do about this 7th decimal if I'm not printing it? So what do you think, what decision do you think it made? It rounded it, right? So it ends up being rounded, ends up rounding, but only for printing, right? Pi was not changed because pi cannot be changed because it is a constant. Printf does not change the values of any variables. It only changes it for the purposes of printing. Fine, I want to see that 7th digit. So let me go ahead and add in one of those modifiers, .7, right? I want to see 7 digits of accuracy. Let's get rid of this comment here. Right. GCC, and run it again. There we go. There's that 7th digit, which is 7, right? And there's my 2, as expected. If you want 20 digits of accuracy, then you could go ahead and bump it up to 20. Is that going to be all that useful? Remember the limitations of these numbers. How many digits of accuracy do I actually have? Only 16 to 17. Let's find out what happens, when I try to print out 20 decimals of accuracy. There we go. So it looks kind of right. But then let's go over to 1 million digits of pi, and that doesn't look right to me. Right? And so, in fact, we can go with an online diff tool. And let's go ahead and, I can get rid of this now. Let's go ahead and copy paste this, put it over here, and I'll just copy the first chunk of this over here. Oops, I didn't copy the 3, so 3 point, there we go. And find the differences. Oh, okay, it's not going to tell me the differences, but you can see the differences already, right? In fact, it's only accurate out to what? 6, 5, 3, 5, 8, 9, 7, 9, 3, and then right there. Right? That's where we get inaccurate. Count up the number of digits there. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 3 is 16. 16 to 17 digits of accuracy. After which, it becomes garbage. I can print out 100 decimals of accuracy if I really want to. But then it's garbage, and then eventually it zeroes out. Right? So what's it doing under the hood? I don't know. That's a question for the compiler writers, whatever they chose to do under those circumstances, because they're free to do whatever they want with undefined behavior. Right? If you're writing your own compiler, you can do whatever you want. Right? What about that other placeholder? Let me go ahead and grab this example, and let's go ahead and use both placeholders. Right? So %10 7f. Yeah, let's go with 15. There we go. No, that's too much. There we go. All right. So remember what this first one does. Let's go back to our notes here. X is going to be the minimum number of columns to print. Let's see the consequence of that. Run it. There we go. So 3.1415972. How many digits was that? Well, 7 digits of accuracy, so 7, plus the period, the decimal, plus 3. I count 9 here. You said you wanted at least 12 columns of printing. So what did it do for you? 1, 2, 3 additional columns right there, right? In other words, it just shifted it over there and padded it out with white space. It right justified it. You can do the same thing if you want a left justification. Just give it a negative value. And we won't be able to see this unless I put something at the end, so I'll go ahead and put foo. Right, there we go. G, there we go. There we go. So where are those 1, 2, 3 additional columns? They're now on the right side because it's justified to the left. And then there's space and foo. Right? So if I've got dollars, double bank account, bank balance, right, is equal to $123.45, right? If I tried to print this out just using the default, right, I have dollars, %F, and the line, bank balance, then what would I get? I would get something that looks like this. Does that look like a regular old bank statement to you? No. So let's go ahead and limit it to just 2 decimals of accuracy using 0.2. Now, if you want a ledger book, right, where you've got a bunch of numbers in one column, a bunch of numbers in another column, a bunch of numbers in another column, like you'll do in your hack a few weeks from now, actually, right? Then you want the decimal places aligned. Using this other one here, 10, 20, or whatever, will allow you to align things left and right. We're not going to be looking for the absolute prettiest output, but we do want it to be readable. Printing out something that looks like this is probably not acceptable because that ain't dollars. Right? So let's go ahead and change it and recompile it, and there. That looks more like dollars. Well, arguably you should put in commas too. If I had $1,000, then I should have 1, 1, 2, 3, right? We're not going to go that far. Right? You can format stuff that way, but it's not worth it. Right? But you can read all about it if you want. Right? All right. There are my examples that I'll bring over here into the notes. There we go. All right. Questions so far? No? All right. Well, something that we've been using just implicitly up to this point is our first operator, the assignment operator. Variables hold values. You need a way to get values into those variables. Right? To do this, you use the assignment operator, which is just a single equal sign. This is not algebra class. A single equal sign in algebra says that the x is equal to a square. What is it? Negative b plus minus square root of 4ac, blah blah blah. I'm gonna have to remind myself because we're gonna use that all over 2a, right? The quadratic formula, right? It's asserting that this thing on the left-hand side here is equal to the thing on the right-hand side here, right? It's a truism that this is either equal or it's not equal. If you have an equal sign and it's not equal, then you slash it out, right? That's not what this means. What this means, it is not on equals as in algebra. Instead, it means take the value of the thing on the left-hand side, LHS, and place it into the variable on the right-hand side, RHS. Right? all it's going to do is evaluate whatever is over here. You come up with a number. That number is then placed into the variable on the left-hand side. The left-hand side can only ever be a single variable in C. Right? There are some languages that you can get fancy with, like Python, and have multiple variables in the left-hand side. And it's kind of useful in a couple of places, but the first time you see it, you go, ugly, and then it grows on you. Right? But anyway, that's Python. We're not going to do that here. Right? So what do I mean by that? Well, let me go ahead and create a couple of variables here. Int a is equal to 10, b is equal to 20. Actually, no, sorry. Let's go ahead and just start with the variables themselves, b and c. Right? First of all, what values are stored in... I don't need any of this anymore, by the way. I've got it in the notes. We can go cut and paste it. I don't want to confuse anymore. What values are stored in a, b, c as of right now? Right? That's a good question. They're just there, right? So in C, an uninitialized variable has no default value, right? In other words, it could be anything. In fact, let me put, instead of putting this in comments, let me go ahead and put this over here. So gotchas, right? Or things to watch out for. In C, an uninitialized variable has no default value. It could be anything. Likely, it will be 0. Why? Because a good compiler writer would probably have put that in there. I'll go ahead and initialize this for you to 0. Right? In fact, if we print these out and find out what they are, I'm willing to bet 10 to 1 here. Printf a is equal to %d and the line a. And I could do the same thing for B and C. B, C, C, B. Right, there we go. GCC, and run it. Yeah, in fact, it is 0. Right? 99 times out of 100, it will be that way. But you get that one compiler writer in that one instance in a million that it doesn't end up being 0. Right? It could be anything. Likely it will be 0, but it could be a trash value. All right, some random value. All right, it could be a value that was left over in memory. Right? It could be what's called dead beef. OX dead beef. All right, there we go. So that's hex speak. Right? Hex speak, you only have 0 through 9 and A through F. So what words can you form out of those things? I can form the words dead beef, right? And dead beef is an old placeholder value to indicate uninitialized memory. Right? In other words, it was just something. It was a joke that somebody came up with, and that's what their uninitialized values ended up being. Right? So instead of doing something sensible and making 0 the default value, they decided, I'm going to go ahead and make it dead beef here to force you to give it a value. Right? And you could be dealing with systems like that, especially if you go on, those of you in EE or CE, if you go on and do systems programming, you'll see little things like that all over the place. You need a signal that this variable or this value or this memory has not been initialized yet. Nobody's touched this yet. Right? Once you set it to 0, it's initialized. You've touched it. And that's a different situation that you might want to deal with. So it could be dead beef. Big question mark. Who knows? Now we actually get to the assignment operator. A is equal to 10. Right? Again, this is not saying, is it a fact, true or false, that A is equal to 10? Right? No, it's saying, take the value 10 and place it into the variable on the left-hand side. Likewise, let's go ahead and do it for B, 20. C is equal to 30. Right, there we go. And let's print them all out again to see that it actually worked. There we go. And it did. Right. Things that will not work are if you say, oh, I want A and B both equal to 10. No, you cannot do. Nonsense in C. Right? This will not even compile. Right? Oh, it will compile. I made myself a liar here. Maybe it's not nonsense, but not standard in C. Right? I'm going to have to look at that again. Anyway, I'll leave that in there. But I will comment it out so that it doesn't affect the rest of our program. I'm not sure exactly what's going on there. It's probably setting B but not A is my guess, but I'm going to cross my fingers on that. All right. Anyway, let's go ahead and do some more complicated stuff. Right? Operators. In fact, let's document that over here. Right? Other operators. Right? Math operators. I shouldn't say math. I should say algebra. Algebraic operators. Right? So if I want addition, guess what? I've got something on my QWERTY keyboard for that. Right? This is addition. If I want subtraction, guess what? I've also got something on my keyboard for that, the hyphen. Right? So this is subtraction. If you want multiplication, look as you may on the QWERTY keyboard, they did not have that little multiplication symbol, right? It is not, say, times. There we go. There we go. That little multiplication system. It is not C dot, right? There we go. The center dot, A dot, B. It's not taking A and B and mashing them together like you could do in mathematics. A, B, you interpret that as A times B. If I did that over here, it would not work. If I set A is equal to BC, right? B times C is how I read that in math. That's not going to work. It doesn't know what BC is. It's going to think that that's some other variable that hasn't been declared yet. So consequently, what do we have on our keyboard that looks kind of like that? The asterisk, right? And that's what we're going to use. That's multiplication. Right? Likewise, we have division. Right? Division. But again, try as you might, you cannot find the division operator, not percent div. There we go. That little horizontal thing with the two dots above it, right? You cannot write it like this, nor can you write something like frac A over B. Oops, there we go. Right? If you were in math, you could just write A over B, numerator, denominator, right? You can't do that in code. Instead, what looks kind of like this thing right here? One of the slashes. Is that a backslash or a forward slash? Forward slash. That's division. Right? All right. Let's try a few of these things. I will set A equal to B plus C. And let's print it out. G. And run it. 50. Why did I get 50? What is B? What was C again? 20 and 30? 20 plus 30 is 50. Checks out. What if I did, say, B minus C instead? There we go. 20 minus 30, negative 10. Note here what I've done. I've reset A now several times. Once I set it up here to 10, then I reset it to whatever the expression is on the right-hand side. Then I reset it again. That's why we call them variables. They vary their value, right? And so each time I reset it, it takes on a new value and it prints on that new value. Right? Let's look at multiplication. A is equal to B times C. What should I expect there? Math majors? 600. What was it? 20 times 30? That checks out. All right. Here's the gotcha, though. What if I want division? So what should it be? It's like 20 divided by 30, right? That should be like 2/3. So 0.666666 off into infinity. Nope. 0. Y. All right. This is another gotcha. Careful. It's called truncation. Right? When you add, subtract, or multiply two integers, the result is always an integer. Right? Right? That's what we just observed. What were 50, negative 10, 600. Right? Well, when you divide 20 by 30, right? When you divide the result of divide two integers, the result is still an integer, right? So, for example, if I say 20 divided by 30, this should be 0.666666, right? But that's not an integer, is it? Right? So what is the integer part of this? 0. What is the non-integer fractional part of this? It's that 66666 repeating, right? So what ends up happening is C will take the fractional part and throw it away. You end up with just 0. Right? This is called truncation. Right? And you don't have the same problem with doubles. Let me come back over here and show you what I mean by that. Let me change the value of these to double. Right? And of course, everywhere that I print out a value here, now I need to change all of these to F's. I'll do a quick cut and paste, cut, paste, cut, paste, 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 and paste. There we go. GCC. Now let's run this again. We're going to get the same whole numbers. What was it? 50.0, negative 10.0, 600.0. But now we're going to get the proper values here. 0.666666. Right? So if you're dealing in fractions, right, then you have to deal in fractions. If you're dealing in integers, you are going to end up with integers, and you do need to be careful about truncation. Let me show you another workaround here. Right? It doesn't all have to be floating point numbers. Right? You do have an argument for using integers everywhere. Right? So this will end up being 0 due to truncation. Right? What I'm going to do is I'm going to show you how to do this properly using what's called typecasting. A is equal to double B divided by C. Now let me show you the issue. Well, this still is not going to work. That's okay. Right? It's still going to be 0 because A is still an integer. So let me go ahead and create a new value, double, I'll just call it Y here, instead of A. There we go. And Y is equal to, and Y is equal to. There we go. And this is not going to be 0 due to truncation. And let me show you for, %F. Thank you, compiler. There we go. Let's run it. And now we get the proper value here. I was dividing an integer by an integer. 20 divided by 30, which is 0.666666, right? But what I've done here is I've said, wait, see, I don't want to lose that fractional part because I'm going to put it into a double over here. So what I want you to do for the purposes of this division, I want you to treat B as a double value so that you don't lose that precision. You don't do truncation. And it says, okay, fine, great. I will go ahead and do that and preserve the value 0.066666. Right? That's what's called an explicit typecast. I am temporarily making B, which is an integer, into a double. Instead of 20, right now it's 20.0. And this preserves the fractional part because of typecasting. There we go. And that's a way around it. The solution is not to throw out integers. You don't throw out the baby with the bathwater, right? Integers are more efficient than doubles. They have a lot of uses. They should be used when you do need to have an integer. But when you need a double out of an integer because you're doing division, then that's when you need to do typecasting like this. Every statically typed language like this has integer truncation. C, C++, Java, C#, et cetera, et cetera, et cetera. It's only dynamic typed languages like Python or JavaScript that don't have this issues. Why? Because you don't have types. You have a variable and you assign it an integer, it magically becomes an integer. You reassign it a floating point value and it magically becomes a floating point value. Sounds nice at first because, hey, there's no guesswork there at all. It's a nightmare because now it's the wild, wild west. If you're writing code towards it and you expect as input an integer, they could give you anything. They could give you a string. And you have to deal with the eventuality that you get bad input. And that's the consequence of one of the huge consequences of dynamically typed languages. So much so that dynamically typed languages like PHP, Python, JavaScript, et cetera, they have stronger statically typed wrappers that will check for things before it actually goes to the dynamically typed. If you've ever heard of CoffeeScript, right? That's an alternative to JavaScript that is strongly typed, or statically typed, excuse me. All right, any questions? Otherwise, yeah, go ahead.
What if you want a remainder?
Good question. We'll do that next time. It's going to be the percent sign. So it'll be A is equal to B mod C is how you would read that. All right.